Hello everybody, my name is Ognjen Mišić and I'm the communication manager of the Group 6 for the OGO Energy Challenge. Along with 7 of my colleagues, we work hard every week to deliver and manifest the most energy efficient driving method for going around the track on the challenge day. Today with me will be presenting Jam, Papine and Water, and together we are going to show you how we divided the roles among ourselves for this project, what we have done so far, how it all went, and what are our plans for the future. We plan on reaching the ultimate goal of this project by calculating the optimal speed at which car can go around the track with consuming the energy from the battery most efficiently. That means with the least amount of energy losses caused by air drag, rolling resistance, and a few other aspects. We plan on doing a few experiments, for example, wind tunnel experiment, dynamometer experiment, and rolling resistance experiment, in which we are going to measure all those resistances and include them in our conclusions and hopefully reduce the air drag of the car. Also, we plan on making some changes on the car itself. We are going to add a rear spoiler and front splitter, which will hopefully reduce the air drag and by that improve the battery consumption. Because organization is the key part when it comes to doing things most time efficiently, we decided to divide ourselves into smaller groups of people containing around 2 or 3 persons working on different tasks and different experiments. We have at least 2 people working on every experiment, the wind tunnel, dynamometer, and rolling resistance, and those people are going to report about how the tests went, and they're going to draw conclusions from that tests, which we are together going to review and figure out the way for the most energy efficient driving method around the track. Also, we divided the roles for the communication manager, equipment manager, and driver himself. Unfortunately, in this group, we didn't have anybody who had any experience with Arduino Duo programming, but 2 brave individuals wanted to stand up to that challenge and enrolled some online courses which will hopefully help them get familiar with the whole concept of how that coding works, and hopefully they will manage to provide us with a good code for the presenting the speed of the car to the driver during the race. Also, so far we have been introduced with all the deliverables and deadlines needed to be made in the next 8 weeks, and we are introduced to the concept of the project itself. But most of our progress so far consists on composing or reviewing and submitting the final versions of our task plans for the upcoming experiments. Also, in front of us we have to do midterm report, final report, and also final presentation, among many other deliverables that need to be done. And as I said, Arduino Duo is one of the biggest parts and most important ones. And we want to try and work even harder on that in the following weeks in order to manage to do all of our tests on time. This was about the progress and the group organization, and now I would like to introduce my colleague Walter, who is going to tell you more about the tests we are going to make.
Yes, thank you. For the dynamometer, Pim and I have been working on a test plan for it. This test gives us good indication about the total power usage of this car. The total test consists of 3 different tests. So we're done with the dynamometer, it can be seen here. In the first test, the dynamometer will drive the car. The car will be disconnected from the battery. This is for measuring the power losses due to the powertrain. In the second test, the car will drive self at the set of fixed velocities and distances. And in the third test, the car won't drive at all. We made some Sankey diagrams for the 3 tests too. You can see it here. Below we see the power input, and every arrow shows us the approximately power flow for each test. In the first test, so like I explained, the car will be driven by the dynamo bench. It will be done with an unplugged battery, so only the powertrain will be driven. By this we can measure the power losses due to the powertrain. In this image, this is the dynamo bench and this is the wheel with the forces in the right direction. So we will drive the car with a constant set of velocities and distances till the next distance is arrived and the velocity will be increased. So this is our free body diagram. In the second test, the car will drive self for the same set of fixed velocities and distances. This is for measuring the total power consumption by the electric vehicle. And when knowing what the total power is and the further losses in the power, we can determine the efficiency later on. And for the third test, we will be measuring the car with no velocity. This is for the idle consumption of the car. The idle consumption is due to the onboard computer and a little bit due to the resistances of the cables on it. So when knowing the input power we measured in test 2 and knowing the loss due to the powertrain in test 1 and also the idle consumption in test 3, we can determine the output power, and it's like this equation. We have the input power minus the power due to the powertrain minus the power loss due to the idle consumption with output power. And when knowing the output power, we can divide it by the input power, and if we divide that, we get the efficiency eta. So it's shown in this diagram. And now I'd like to give the word to Pijn for the next test.
Thank you, Wouter. The aerodynamics test, our goal will be finding the air drag coefficient. We can find it with the formula for the air drag force. It's presented here. All the variables in the formula are from left to right: air drag force, air density, air drag coefficient, frontal area, and velocity. By knowing all the values except the air drag coefficient, we can calculate the air drag coefficient. So we are trying to find all these variables. The air drag force we will find with doing the aerodynamics test in the wind tunnel. The air density will be constant in the wind tunnel since the temperature does not change and the humidity in the room does not change. Only the pressure can change a little bit, so we will have a look at the pressure at that day. The air drag coefficient is the one we are trying to find, so we will need all the other variables to find that value. The frontal area, we had a hard time finding this value, but we started off with finding the frontal area of the Audi A4, which the model car is based on. The only problem was that the width was more and the height was less than the scaled down version of the Audi A4, so we had to come up with a way to measure it on our own. So what we did was we looked up for some software which can calculate the frontal area. We first made a picture of the car from as far away as possible so we wouldn't get much perspective. And in this software we outlined the outlines of the car and gave a base distance from the outside of the wheel which we measured, so the program would know at what scale it's working, and with that the program gave us the frontal area of the car. The last variable is the velocity. We got a formula for the velocity in the wind tunnel, and we calculated the pressure for the velocity. So at the test we only have to match the pressures which are presented here to get the velocities 30 and 50 kilometers an hour. We first wanted to have 5 measuring points per setup of the car, but this would take too long, so we decided to have 2 measure points at the first test. And if it turns out that the drag coefficient is very equal to at 30 and 50 kilometers an hour, we will only do the 50 kilometers an hour on the other tests. So the setup will be, the model car will be placed on a platform which can move back and forward freely, and will be connected to a force sensor which gives the air drag force created by the air that's pushing to the car. And this will be the entire setup with the car in here. So if we have all these values, we can calculate the air drag coefficient by rewriting the air drag force formula. That was it for the aerodynamics, and now I give the word to Jack.
Our goal was for rolling resistance test plan was to write a test plan which we can calculate rolling resistance coefficient. But first of all, what is rolling resistance? Rolling resistance is the force on a rolling object that works opposite to the direction of velocity, and it depends on many things like surface of tire, temperature of tire, velocity, and weight on tire. And mainly it's the main component of energy losses in lower speeds which we will work with. We all knew this as we were automotive students, but we didn't know how to continue from that point, and we decided that first we should decide on the experiment procedure so that we can continue from that point. And after doing a lot of research, we found out that we have 4 options in terms of rolling resistance experiments. First one was the trailer method, which you can see here, but we couldn't perform rolling resistance experiment because we needed force sensors, as you can see here, and so we had to, it wasn't an option anymore. And for the second option, it was the drum test of tires, like here, but as you can see in this picture, it is performed only with the tires of the car, not the whole cars, and we couldn't take out the wheels of our car, so we had to, it wasn't an option anymore as well. And third one was full compensation method, and it was too complex for us to perform. And the fourth one was the constant method, and it was simple enough for us to perform. After choosing our procedure, we decided that we should decide on our main variable so that we can make changes to our default setup of cost down method, and so that we can change the variable. The variables that we thought of was velocity, tire surface, temperature of tires, and downforce. And tire surface, we couldn't change it, so we had to ignore it. And for the temperature of tires, we couldn't change it as well, so it was no more an option for main variable. We decided that our main variable should be velocity, considering the size and the mass of the car. Other than these variables, velocity, the rolling distance coefficient mainly depends on velocity, and if we have time, we decided that we can we are going to change the downforce of the car by adding splitter and spoilers. After deciding on our main variable, we had to make changes to our setup, as you can see here, so that we can try different velocities between different trials. As you can see here in the setup, the car is released from a specific height, and it goes down the wooden inclined plane, and it continues for a time, and after that it stops. So we had to find a way to change the velocity between trials, and since the only force that was acting on the car was gravity, we had to change the height. But as you can see here, at the top of the inclined plane, it has no kinetic energy but only potential energy, and down at the end of the inclined plane, it has no potential energy but kinetic energy. So all of its potential energy is converted to kinetic energy, and if we equate these two with the law of conservation of energy, we can actually find the height that we need in order to obtain our desired velocity. After making changes to our setup, we had everything ready, but we had no idea how to calculate the rolling resistance coefficient. We knew that we had the data, velocity and time data from our Arduino, but we had no idea how to use them so that we can find the rolling resistance coefficient. And after doing research, we realized that the car is stopped by the rolling resistance force. Its energy, it stops because of the work done by the rolling resistance. So the energy change is equal to work done by the work of the rolling resistance, and since we know that the car stops at the end, it has no energy, and its initial energy is only kinetic energy, because on the floor it has no height, so it has only velocity, so it has only kinetic energy. And if we equate them, we have this equation right here, which it seems that we don't have enough data, and we have a lot of unknown variables, but actually we have the velocity data from our Arduino, and we can actually calculate the distance by plotting a velocity time graph from the data that we obtain from our Arduino. And if we plot a velocity time graph by taking integration, we can actually find the distance that it takes for a car to stop. So since we know all of this, with a little bit calculation, we can obtain the rolling resistance coefficient very easily. And the only thing that we need to determine is the velocities that we actually want to try with the car. And now I would like to give the word to my friend so that he can end the presentation with conclusion.
Thank you. These were the plans for the upcoming experiments, and in front of us during the next couple of weeks we have a lot of tests to be done. We had to do experiments themselves, get some results out of them, and draw conclusions out of the results we got. Also, we have to do a midterm report. We have to do as well as final report and final presentation. There is a lot of work ahead of us, but I believe that if we stick together and if we continue on working the way we worked so far, that we will have no problem finishing the project itself with good results. What makes me so confident about our work is the fact that in the past 2.5 weeks we did not miss any deadline, and we even got plans and reports ready even before the deadline, so we can check them together and improve maybe something. When it comes to finishing the project itself,
We still have, as I said, a lot of work to do, but we are all here because of our passion about cars. We all chose this project because we want to do something like this in our future, and we are all willing to put in some extra hours into meetings and learning in order to get this thing done as good as possible. Hopefully you now have the idea of what we have done so far and what are our plans for the future. Hopefully you enjoyed, and thank you for your attention.